Good deal. All right, well, why don't we get started here? Thanks everyone for joining us today. My name is Brian Hesterman with Inspire, and I'll be hosting today's webinar and Q&A session. We're here today to talk about mechanical systems for indoor plant environments. And as the title suggests, growing cannabis inside a sealed room is a highly complex interdisciplinary challenge that bridges engineering with biology. We're adding and removing energy inside these cultivation rooms to balance and optimize the growth of living organisms, in our case, cannabis plants, whose needs are constantly changing. And through the lens of increased competition, price compression, and shifting consumer preferences, carefully designing a facility will determine the success or failure of today's cultivators. It truly takes a village to build a high-performing cultivation facility, and for that reason, we have a diverse audience in attendance today. Architects, engineers, contractors, cultivators, owners, investors, consultants, and the network of channel partners we collaborate with every day. Today's presentation is part one of a two-part series and will be focused on the biology side of the equation, the plant. This will be new content for some and review for others, and we'll do our best to lay a solid foundation of plant science concepts, dynamics of a sealed grow room, and HVACD system sizing and selection, with the overall goal of building better facilities and growing better cannabis more efficiently. A couple of quick housekeeping items. Part two will be on the mechanical systems and cannabis-specific sequence of operations that we apply to optimize the plants inside these cultivation facilities. We'll also talk through setting baselines and expectations for an application that doesn't currently have any. Please register for part two using the link in the chat. We'll drop it in the chat here momentarily. For today's session, you can find the Q&A section at the top of the webinar screen. Please ask questions as they come up, and we'll do our best to answer them at the end of the presentation. Today's webinar will also be recorded and uploaded to YouTube so you can rewatch later. Today's webinar will be presented by Inspire's Cannabis Operations Specialist, Anders Peterson. Inspire's Adrian Giovenco will be joining for Q&A after the presentation. And without further ado, I'll pass the mic over to Durs. Take it away, my man.
Thanks, Brian. Hi, everyone. Thanks for joining me today in today's discussion. My name is Anders Peterson, affectionately referred to as Durs by a lot of my friends and colleagues. I'm a biologist and have been working in the cannabis industry for almost 12 years now, with a focus on indoor cultivation. In part one of this webinar, I wanted to share with you some of the core concepts about mechanical systems for indoor plant environments that I wish I knew as a cultivator at the beginning of my career. But there's really no easy way around it. Some of these are complicated topics, and there's even going to be a little bit of math. So I'm going to try my best to simplify everything and break it down over the next 30 minutes or so. And I encourage you to reach out to us here at Inspire if you have follow-up questions or want to learn more about a particular topic. So setting the stage a little bit, this talk's going to focus on environmental control for indoor cultivation, not greenhouses. Many of the concepts still apply to greenhouses, but they have their own unique considerations. Keep in mind, too, as we go through this talk, that these are tightly sealed grow rooms with no outdoor air being introduced to normal operation. Everything is fully recirculating because we are also supplementing CO2 into these spaces. And finally, our talk today will focus on the cultivation of cannabis. But again, these concepts can apply to pretty much any crop grown indoors with their own, unique species considerations. So let's quickly review the main parameters of plant growth that we are trying to control in these facilities. In one way or another, your HVAC system impacts everything you see here. In the shoot zone, we have light, temperature, humidity, CO2, and airflow. And in the root zone, water, oxygen, root zone temperature, and nutrients. Microbes as well, while not essential for plant growth, they should be considered with their ubiquity in our environment. And last but not least, running down the center of that plant is genetics, the foundation of everything. Genotype plus environment equals phenotype. Or in other words, the genetics just represent the potential of a certain variety. The better the environmental control, the better the phenotypic expression at the end of the day. If If you want to learn more about phenotypic expression, we actually have a whole webinar dedicated to this topic on our website. And I believe Brian's going to drop it into the chat if you'd like to check it out. Now, none of these parameters exist in a vacuum. They all work synergistically. The plant's health, growth rate, and yield depends on which of these parameters is its greatest limiting factor. This concept is called the law of the minimum and is often depicted by this barrel here leaking water or yield on the right. Essentially, you are only as strong as your weakest link, like the shortest stave in the barrel. And for each species of plant, there are optimum targets and ranges for each of these parameters to maximize the plant's growth rate and yield. And these optimum conditions change as the plant develops, from a young vegetative plant to a mature flowering plant. And some of these parameters, the optimum condition can change on an hourly or minute by minute basis. Compared to growing plants outdoors or in greenhouses, a grower's ability to control and optimize these parameters indoors is exponentially greater, and you can really push plants to their limit. You know, cannabis is quite an amazing plant. It will grow like a Toyota Camry if you treat it as such, or it can perform like a V12 Ferrari depending on how hard you push it and can dial in and control these parameters. And so much like this law of minimum for plant growth, the productivity of an indoor facility is determined by its greatest limiting factor as well, or its most underperforming system. And in my experience, the greatest limiting factor for most indoor facilities today is their mechanical systems, or their ability to control the temperature and humidity of their rooms. Not very long ago, I would have said the greatest limiting factor was lighting. But with the advances in LED technology, I just don't think that's the case anymore. And that the improvement of mechanical systems presents the greatest opportunity to maximize the productivity of indoor cultivation businesses. And this is exactly why Inspire was founded, to develop purpose-built systems and controls that are assets and tools for growers and not a liability. So to maximize the growth rate of a plant, we must maximize the rate of two main plant processes, photosynthesis and transpiration. I think it's pretty safe to assume that most of you are familiar with photosynthesis, the conversion of light energy into chemical energy in the form of sugar. So I want to focus a bit on transpiration. So transpiration is the movement of water and nutrients from the roots through the shoots and then to the leaves, where the water then evaporates from a liquid to a gaseous vapor. About 97 to 99% of the water a plant absorbs through its roots is lost through transpiration and gets added to the air as water vapor. So therefore, transpiration is the primary source of humidity being generated in a sealed grow room that a mechanical system must remove by dehumidification. And transpiration and photosynthesis are separate processes, but are intrinsically linked since they are both regulated by the opening and closing of the stomata, which are little pores found on the underside of the leaves that have the ability to open or close depending on the environment and are where all the gas exchange occurs. So CO2 enters while oxygen and water vapor escape. As water evaporates from this stomatal cavity, there is what's called a net cooling effect. As these molecules evaporate, they are taking heat energy with them, and the result is a cooler leaf surface than the air around it. And you can measure the leaf surface temperature. And if the leaf temperature is cooler than the air around it, it generally means the plant is actively transpiring. For example, in LED flowering rooms, the leaf temperature is generally 3 to 5 degrees cooler than the air around it during the lights on period because of this net cooling effect of transpiration. And the rate or speed of transpiration can change. It can be fast, slow, or stop altogether, depending on pest pathogen pressure, the amount of light, how much water is in the root zone, if the stomata are open or closed, and the combination of temperature and relative humidity, or what's called VPD. So transpiration, this process of water going upwards into the plant, is not going to happen on its own. There's no magical plant pumping mechanism to force water up through its stalk. Instead, the water is actually drawn up through the plant by the environment and the vapor pressure deficit around the leaves. VPD, typically measured in kilopascals or kPa, is the pressure the environment places on the leaves to draw water and nutrients to the upper part of the plant, where it can then escape from the stomata as a vapor. I think of this VPD pressure like the pressure you create with your mouth when you're drinking through a straw. Technically speaking, VPD is the difference between the amount of moisture in the air and how much moisture the air can hold when it is 100% saturated. And you can visualize this on what's called a psychrometric chart, like the one here on the bottom left, by plotting the room conditions and the leaf temperature, and then subtracting the associated vapor pressures of each condition to get the deficit. There's an optimal range for VPD depending on the stage of growth the plant is in. And generally for cannabis, from propagation to harvest, we are talking a range of between 0.5 and 1.5 kPa, shown in that table there in the center. So with a high VPD, the air is really dry and has lots of room to accept more moisture. So the water in the stomata will want to evaporate to an area of lower concentration, and the transpiration rate and water demand on the plant will increase. With a low VPD, the air around the leaf is really humid and there isn't much pressure being placed on the leaf to transpire. So the transpiration rate and water demand decreases. Research shows that the tighter you can control VPD and reduce fluctuations during a plant's life, the more productive it will be, and significant yield increases can be achieved. With the appropriate mechanical systems, 24/7 VPD control is possible and can lead to these significant yield increases. Lastly, there seems to be a lot of confusion around VPD amongst growers that I'd like to try and address, and it surrounds leaf temperature, VPD charts, and getting an accurate VPD measurement. So when touring facilities, I often see a VPD chart printed off the internet and taped up to the wall. The grower then checks the temp and relative humidity from the sensors in their room and uses the chart to figure out their VPD. The problem with a static chart like that is they almost always assume that the leaf temperature equals the air temperature, which we know is not always true given the evaporative cooling effect of transpiration. So they get an approximate VPD, but this can be pretty misleading. Essentially, most growers are not measuring their leaf temps and factoring it into the equation. And that's fine if you are in a greenhouse, for example, where the environment fluctuates so much more on a daily basis than a modern day indoor grow, that an approximate VPD is good enough. But with the highly optimized indoor grows with good environmental control, we are pushing these plants' transpiration rates to the limit, which increases that evaporative cooling effect of transpiration and drops the leaf temp to a greater degree. So look at these two example calculations. On the bottom, the one on the left assumes the air temp equals the leaf temperature, and you get a 1.2 VPD. And on the right, the leaf temperature is factored in at 5 degrees lower than the air temp, and now you get a VPD of 0.7. So without factoring in leaf temp, you might think you are providing your plants a good condition for mid-flower, when in reality, your plants are feeling a VPD more conducive to vegetative growth. A difference of 0.5 is significant in VPD terms. And so somehow this kind of confusion around using leaf temp or not resulted in the terms air VPD and leaf VPD being coined, where AVPD does not factor in leaf temp and the LVPD does. But in reality, LVPD is the true VPD and the true pressure that the plant feels to transpire. And I highly suggest all indoor growers measure leaf temperature. So really quickly, same type of example, but on a VPD chart. This VPD values on this chart assume leaf temperature equals air temp. And the blue region is a target range of 1.0 to 1.5. And our example room is sitting at 80 degrees, 60% relative humidity in that red box with a VPD of 1.4. Okay. Now look, room is still at 80, 60, but the values on the VPD chart have been recalculated, taking a -5 leaf temp offset into account. Look how the blue region has shifted, and instead of a 1.4 VPD, we are actually at 0.9. Again, just highlighting the importance for indoor cultivators that leaf temp should be measured and tracked and helps dictate your set points in your room. Okay, moving on. With indoor growing, we have all these growth parameters and plant processes going on within a very tightly sealed box. And this creates a highly dynamic space with a lot of rapid changes to the environment. Particularly, flower rooms generate substantial and dynamic loads, both on a daily basis and over the course of a harvest cycle. Compare that to an office space or your home where the conditions are fairly static. They don't change that frequently or dramatically. And to design and operate efficient HVAC systems, we must understand the dynamics that are happening in these spaces throughout a harvest cycle. Or left uncontrolled, these drastic changes in the environment lead to poor plant health, quality, and yield. Growing at the end of the day is all about maintaining balance within the system, within the room, and within the plant itself. So from a mechanical system point of view, the water balance in these rooms is particularly challenging to manage compared to other HVAC applications. There are not many other indoor spaces that require as much dehumidification as indoor plant environments. And this graphic highlights just some of the moisture dynamics that must be considered when designing and sizing a mechanical system. There's a lot going on, but all of this can be quantified to size the dehumidification requirements. By understanding the plant processes and the variables that affect these dynamics, we can engineer a solution to balance them. So for example, growth phase and plant age on the upper left. As plants grow and get bigger, their water demand increases and they transpire greater volumes of water into the space. Transpiration rates can increase almost 40 to 50% over the course of a flowering cycle. So this is where variable capacity HVAC systems with modulating components and the right control sequences become really important so that you don't overcool or over dry the space during partial load scenarios. In the middle, the photo period also affects the moisture dynamics. Plants transpire a majority of the water into the air when the lights are on and they are photosynthesizing. In a flower room, about 75% of the moisture needs to be removed during the lights on period and about 25% during the lights off period in a given day. The lights on to off and off to on transition periods are by far the most challenging dynamic shift that a mechanical system must control. As the lights turn off, the temperature drops and the relative humidity spikes, which requires an immediate and significant dehumidification requirement. This spike can be overcome, again, with things like variable capacity systems, appropriately sized reheat, and purpose-built controls, which are things that come standard in Inspire's units. The PPFD, or light intensity on the upper right, also greatly affects the moisture dynamics in the space. As the PPFD increases, the water demand and transpiration rates increase as well. With the newer high-intensity LED fixtures today, growers are pushing their PPFD higher and higher to increase yields and shorten cycle times. So for many years, 1,000 to 1,200 PPFD in flower was the standard. But now many growers are designing and building rooms at 1,500 plus PPFD, all the way up to 2,000, and pushing the light limits. So if you are planning on a high PPFD strategy, your mechanical systems must be upsized accordingly to handle the higher transpiration rates, or you will not be able to maintain humidity control. So sensible and latent loads are how we are going to quantify these dynamic needs of an indoor plant environment and appropriately size an HVAC system for a given room. Inaccurate load calculations lead to undersized or oversized equipment, which both present challenges. For most HVAC applications like offices, residential homes, or even gymnasiums, there are published standards from industry organizations that engineers can refer to for guidance when calculating loads. However, with the nascency of the cannabis industry, no good standards currently exist for indoor plant environments for engineers to refer to. Luckily, that is going to change. Ourselves and a number of other colleagues in this working on this application with industry organizations are looking to publish those in the coming years. For now, I'd like to go through an example load calculation and the system selection process to better prepare you for your next facility build out. There are two types of loads we must calculate to size a system. The sensible heat load, which dictates our cooling and heating requirements, and the latent heat load, which gives us the dehumidification or humidification requirements. And as we go through this example, keep in mind that I have simplified some of these calculations for the purpose of this webinar, and other variables not shown here are considered when doing this in practice. I didn't want to put you all to sleep or scare you away with too much math. So for this example, we're going to use a relatively small flower room. Sensible loads include anything that generates heat we can feel within a grow room. Horticultural lighting fixtures account for 95% or more of the sensible load in indoor plant environments. Any other appliance within the space that uses electricity will also add to the sensible load, such as fans or irrigation pumps. Many rooms also have standalone dehumidifiers hung within the space, which generate a lot of waste heat while dehumidified in the air. At Inspire, we design and sell what we call integrated HVACD systems that incorporate that dehumidification capacity into the HVAC system, removing the need for standalone dehus in the room, hence the D in HVACD to emphasize dehumidification. And Adrian will discuss this in greater detail in part 2 of the webinar in a few weeks. Okay, for this example, we have 32,000 watt HPS fixtures in our flower room. We calculate the total wattage of all the fixtures and then convert watts to BTU per hour, which is a measure of energy in the form of heat. And we get a large number. So we divide by 1,000 to make it more manageable to work with. And the result is of our sensible load is 109.2 MBH, or what's called mega British thermal units per hour. MBH is really the most common units. But if we went with the same number of more efficient LED fixtures at 700 watts and do the same math, we now get a sensible load of 76.4 MBH, which is a 30% reduction in the sensible load compared to HPS. So I want to use those in my flower room. They're more efficient. I'm going to have a lower operating expense because of it. So the latent loads are where an understanding of plant science, cultivation, and room dynamics become necessary. With no published standards, we came up with this formula at Inspire to calculate the latent load. The math itself is simple, but inputting the right values for each of these variables and understanding how they affect the system sizing is why we built a multidisciplinary team of plant scientists, cultivators, and engineers, and take a collaborative approach with our customers to understand their cultivation strategies. Establishing an open line of communication with the cultivators early in the design phase goes a long way in right-sizing these loads and systems. The result of this calculation gives us the pounds of water per hour moisture removal requirement for a given room. It's important that we target the maximum latent load that room will generate over its operational lifespan to future-proof the design and provide the right capacity. The most crucial step in this process is getting an accurate total daily watering rate in gallons per day there at the top. While it's labeled watering rate, it's better to think of this as the maximum volume of water transpired by the plants into the air in a day, for a given room. Seemingly what you would think as small changes to this value can result in drastically different unit sizes and costs as these rooms get bigger and bigger. The total daily watering rate can be calculated on either a gallons per plant basis or on a gallons per canopy square foot basis, the total surface area of all the trays in the room. The canopy square foot route is preferred because once these rolling benches or multi-tiered racks are installed, it is a fixed variable and doesn't change. While the plant count often changes once the facility is up and running. And sometimes I've seen it fluctuate by as much as 15 to 20% from the design phase to what's actually being done in the field. So I like the canopy route. So for this example, we have our same relatively small flower room with 512 square feet of canopy. We have a 0.26 gallons per square foot watering rate, giving us 133 gallons per day. Next, we plug that into the equation from before, and we get a latent load of 69.3 pounds per hour moisture removal requirement. So we have that 75% moisture removal during the day we talked about, the 12-hour photo period, and then we use the 8.33 to convert pounds from gallon to pounds. So we can also convert pounds per hour to MBH, like in our sensible load, to get 74.8 MBH as well. And that is the latent load of our room in two different units, pounds per hour and MBH. And in summary, this example flower room has a sensible or cooling load of 76.4 MBH with those LEDs and a latent or dehumidification load of 74.8 MBH. Engineers would describe this room as having a sensible heat ratio of 0.51, meaning 51% of the room load requires cooling and 49% requires dehumidification. Most comfort cooling or human-centric HVAC applications have an SHR closer to 0.85. They require almost all cooling capacity out of the equipment. And as a result, almost all HVAC units today on the market have an SHR of about 0.85, with 85% of their total capacity going to cooling and only some going to dehumidification as a byproduct of the cooling process. So this SHR here is why we had to design purpose-built integrated units to serve indoor plant environments, because they really have a different need than most other spaces. The final step in the system selection process, now that we have the loads calculated, is to find a unit that can meet the required capacities that we've run in our load calcs at the temperature and relative humidity conditions that the cultivator is realistically going to run the room at. These are called the design conditions during the system selection process and can lead to over or undersizing a system as well. For all HVAC or mechanical systems, it is easier for them to remove moisture from the air at warmer temperatures. So as selection temperature and RH decrease and room conditions decrease, you need a bigger and larger capacity unit to meet that load. This table shows an example unit's moisture removal capacities in pounds per hour at various conditions. This is the performance data for this unit. And from 8270 on the upper left down to the bottom right to 6550 following that green line, this unit's moisture removal capacity decreases by 80%. There are significant derates depending on the design conditions and the room conditions this equipment's operating in. But at 7555, a reasonable condition to run a room at, this unit can do 77.4 pounds per hour, which meets our 69.3 pounds per hour requirement from our example. So this unit would probably be a pretty good fit at the right design conditions and has the capacity to meet that latent load. Now, in practice, this is done by software that has the performance data for every unit at various conditions to find the best fit for a given load. The design conditions present a delicate balance between the range of set points or VPD targets a system can achieve and the overall cost of the system. As the design conditions go up, the temperature and relative humidity go up, the ability for a system to remove moisture goes up. And so the required unit size goes down along with the cost. But the grower's ability now to hit all those VPD targets also goes down, and you lose some set point flexibility and you run the risk of undersizing the system. And vice versa when it comes to oversizing. Lower those design conditions, lower the moisture removal capacity of equipment gets, bigger the unit, and the connected electrical, structural support required, the costs, but you get some greater set point flexibility. So you have to find a very good middle ground to balance these things. You can have the most accurate load calcs in the world, but with the wrong design conditions, you really run the risk of increasing the CapEx and OpEx for your project or undersizing the system, resulting in poor plant health and yields that are really hard to overcome once the systems are installed, and require a much higher labor cost to manage. The table on the bottom here are design conditions I recently got from a customer for an LED flower room. And so for the lights on period, they wanted to be able to hit 75-50 minimum and 85-65 maximum. So as an exercise, I calculated the sensible and latent loads for these rooms, and I ran the selection through that software we talked about at both conditions, both 85-65 and 75-50. And going from 85-65 to 75-50 doubled the size of the system and doubled the cost. So at the end of the day, we settled on a middle ground of actually 78-55 for the design conditions for this room, which will allow them to hit 75-50 at the end of the flowering cycle when they want to, when transpiration rates have started to subside, without blowing up their budget and getting them too big or too small of a system. And that, folks, is an overview of how mechanical systems are sized and selected for indoor plant environments and some of the core plant science concepts to understand. I wanted to just introduce to you some resources if you're interested in learning more. On the top there are some of my favorite books, and in the middle there are some great industry organizations that are doing valuable work. We work, at least one person in our company is involved in one of each of these organizations. I highly recommend checking them out and becoming involved to help push this application forward. And as well, you can check out the resources page on our website, where there's a number of other webinars and articles, along with some calculators with these formulas plugged into, so that you can, play with them. And use us as a resource. We really want to get into these projects early and help you through this process to size the best system possible to produce the most control and the most efficient indoor facilities. Earlier, the better, so that we can start engaging. There's a lot of considerations with HVAC systems at the get-go of a project that are useful to consider. As well, I think we're going to drop a link in the chat to reach out to us for a free consultation on our website if you'd like to dive deeper into any of these topics discussed today. And we also are going to, I think, throw a link in for a system that we call our Room Wizard. And essentially, it's a website that allows you to enter these various variables for a room or a facility if you have a project, and it automatically calculates these loads and puts them into our system, where we can then follow back up with you with some preliminary sizes and budgets. So go ahead and play around with that as well, and we'd love to get some feedback on it, on that tool, that Room Wizard link. And that really concludes today's presentation. Thank you for listening. I hope you learned something today and found this useful. We're going to move into some Q&A and answer some questions before we wrap this up. And I think Adrian's going to join me during this Q&A session as well. Thank you.
All right. Great job as always, Anders. Thank you very much.
Thank you.
Trying to turn my camera on here. This is our first time using the Teams webinar platform. I think so far so good. There we go. Hope everybody was able to follow along and didn't have any technical complications. So let's see here. I've got a couple of questions sitting here in Q&A that I think we can start with that are really good. The first one is, do you have recommendations, best practices for measuring leaf temperature, and particularly how to do it in a way that feeds into a control system?
Yeah, that's a good question. Funny enough, I actually have my IR gun here, which is the manual method of measuring leaf temperature. So this is an infrared thermometer for manual measurements of leaf surface temperature. A thing to note about measuring leaf temperature with a tool like this is every surface out there absorbs radiation at different rates and reflects it at different rates, and that's called emissivity. And so when you get one of these guns, you want to make sure you get one with adjustable emissivity setting, and an emissivity of 0.97 is conducive to getting an accurate leaf temperature measurement. Most plants are between 0.95 and 0.98, and all the research I can find suggests that a 0.97 emissivity gets you the most accurate measurement. So what I do is you go through a room and you stand with a gun about 12 inches away from the leaf surface perpendicularly. That gives you about a 1.5 inch measurement diameter on the leaf surface. And you want to take these measurements at multiple areas throughout a room to get a statistical average of the space. And I like to do that in the middle of the photo period, like say 6 hours into a 12-hour photo period to get the most consistent results every day. And then I average all those measurements and use it to dictate my set points and how I run my system and what VPD I'm at. Now, about integrating in a control system, there are a lot of ways to do this automatically without a manual measurement. It's especially today as these sensors and the IoT things has gotten so much cheaper. And so there are a couple different approaches. There are cameras that try and ignore the ground and the benches and hit only the canopy to get a good measurement at the right angle. And then there are also like leaf calipers that almost have a little thermistor underneath the leaf to measure the temperature. You can plug a bunch of them in around the room. Those are both ways in which you can automatically monitor and data log it in a space. Yeah, leaf temperature. I love it. It's one of my favorite topics. So many cool things you can do with leaf temperature. In fact, I even use it to time my irrigation events, like in P1 events of crop steering. You can sit there and measure leaf temp or look at your water content in your substrate. But as lights turn on and that starts to drop, leaf temp drops, the water content drops, transpiration has begun, and you can start irrigating your plants.
Very cool. So, and I think related to that question is, can your leaf VPD change every couple minutes within a room with a stable environment?
With a stable environment, that's an important distinction. If the room doesn't have homogeneous airflow, then the leaf temperature will vary throughout a space. Essentially, the faster the airflow a plant is getting, the more convective buoyancy flux, essentially, and the transpiration rates will increase. So in areas of stagnant airflow, you'll typically see higher leaf surface temperatures. They can change, but not that rapidly, actually. So the reason being is the plants have developed these processes to balance themselves. And so the leaf temperature is actually much more stable in a space than the air temperature is because the plants are using that stomata and transpiration, that cooling effect to balance it.
It's that concept that plants are immobile organisms, right? Humans can get up and run if it's hot or dry or too cold, but plants have adapted processes that allow them to adapt to the environment where they are because they can't move.
That's right. Yeah, they've had to develop these things like stomata opening and closing to protect themselves in unfavorable environments where we can just run away.
Yep. Very cool.
My sweater.
Let's see.
Do you want to? There's one last one on leaf temperature and just differences between does it vary between HPS and LED? Maybe is a good finisher for that topic.
Yeah, sure. So typically, because of the infrared radiation or the radiant heat that these HPS fixtures give off, oftentimes the leaf temperature can be higher in HPS rooms or the offset be less than in LED spaces. But that is not always consistent depending on the lighting design and room design. So depending on the mounting height of those lights, how big the space is, because for example, a colleague of mine, an engineer, Chris Webb, he has a great saying that the larger the biosphere, the slower the changes, and the smaller the biosphere, the more rapid the changes. And so same thing with these leaf temperature and HPS versus LED. With a bigger space, lights further away, the environment can kind of balance itself and respond a little bit slower to environmental changes than in a smaller space. But I've seen in rooms with HPS lights, the leaf temperature be higher than the, the room conditions. And therefore, that's why a lot of HPS rooms have to run their their set point's a lot lower to offset that. And so one of the big benefits of LEDs is you can run your rooms a lot warmer and maintain the same leaf temperature. And it just saves you money on your, utility bills every month as well from your HVAC system.
And potentially the CapEx spend up front if you don't have to size your systems as aggressively.
That's right. Yeah. You don't have to, those design conditions are more amenable with LED rooms than HPS to give you that control.
Awesome. Thank you. Here's another good question. What are the advantages, disadvantages of having single or multiple HVACD units servicing the same cultivation environment? Do you prefer one large unit or multiple small units, and why? I understand this may be dependent on particular conditions for that space.
Yeah, that's a really good question. I'm happy to touch on that a bit. And I think Adrian actually in part 2 in a few weeks is going to go into greater detail on that question. But really quick, there's pros and cons of each, right? Having multiple units can have a benefit in terms of redundancy, which is sort of a, what's the right term, Age? Like a redundancy. It's kind of it's a subjective term, right? Of what redundancy means in the cannabis industry with equipment. And so having multiple units can have its benefit, but it also makes control and compressor staging a little bit more complicated, and it increases the installation cost because you just have more ductwork to run, more power drops, more gas drops, and can make it a little bit more complicated. But with a single unit, you can reduce some of those costs. The controls become a little bit more simplified, and yeah, you might have less units in terms of redundancy, but a lot of redundancy can be built into a single unit by adding multiple refrigeration circuits, so that if one goes down, you still don't lose all your capacity. And a critical part like spare parts on the shelf just in case, and regular maintenance. So it really depends. Again, it's all a balance between risk reduction and cost, basically.
Yep. Yeah, I think you really nailed it there, Anders. It's a wide range, and it's really understanding what does redundancy mean for a particular cultivator or cultivation business. Really, most importantly, first, and try to start there, understand what the budget requirements or restrictions might be around it. I think the overall system size and scale offers ability to, in many ways, more inexpensively include additional points of redundancy into a system than it may on a smaller scale, or with a hydronic type system, as an example, compared to individual DX type units, packaged units, or split systems. So there's a lot of different factors to consider there, and it really is us putting on our owner's hat and our fiduciary hat, as if it was our money, and working together with both the design team and the ownership group to really come up with the right solution. But we see a really wide spectrum of ways to combat redundancy or backup, risk reduction, risk mitigation, really, as it comes to that at the end of the day. And I'm really glad, Anders, you brought up preventative maintenance and the necessity to maintain these systems. These systems should work and operate as designed for their useful life all the time, as long as they are well maintained. And that's the caveat there that you really always have to make sure that you're staying in front of.
Can't set it and forget it.
Yeah, just like plants, you can't ignore them. They need to be cared for and serviced and maintained, just like the system serving them.
Good deal. Well, more on that November 9th. And reminder to everyone to go register for part 2. The link is in the chat. Got another good question here on the dynamics of these spaces and the transition between lights on and lights off. Given that the transition from lights on to lights off is such a great struggle for mechanical systems, do you see any reason why it wouldn't help to dim on and dim off over a period? For instance, the first and last half hour of the photo period, so the spike in temps are not as severe.
Yeah, that's a good question. basically sunrising and sunsetting your lighting fixtures to not have such a dramatic and drastic heat change or heat gain in the space. Yeah, I mean, again, there's pros and cons to that. From a mechanical system perspective, it can be a pro because you are easing that load in and allowing that unit to catch up a little bit easier in terms of its capacity and ability to its speed to hit set point. However, from a plant perspective or an optimizing a cultivation perspective, every time you dim your lights, you're sacrificing the total daily photon uptake of your canopy, or what's called the DLI. And so every time you sacrifice light, you sacrifice yield essentially by a little bit every time. I've personally, as a cultivator, never been a fan of sun rising and sunsetting my lights. I like to go full bore at lights on, full bore lights off. But that's if I have the right mechanical systems. And I just want to maximize that DLI and total amount of photons that hit my canopy per day. So there's situations for all of them. The way I think about it is things like ramping up and down is a tool. And so if it requires it, yeah, use it as a tool, as a grower in your back pocket. If you don't need it and you can maintain set point, push your plants, push them hard and get that yield.
That's awesome. It's a great answer. Got another one here. Is there significant heat gain from the plants that should be considered in the sensible load? Also, the sensible calc assumed all light wattage contributes to the sensible load. Should a factor be applied if a lighting manufacturer can provide the actual heat given off, or just assume worst case scenario?
Yeah, so 2 questions there, both good ones. H, how about I handle the first one? You want to handle the second?
Sure.
Sure. So is there a heat gain from the plants for the sensible load? Well, because of the evaporative cooling effect of transpiration, they actually have a cooling capacity associated with their canopy when they're transpiring. Plants aren't necessarily generating any heat. They're actually cooling the air around them. I've actually, as an exercise, calculated how many square feet of canopy can equate to 1 ton of cooling capacity, and given like theoretical maxes in flowering under of transpiration under 1,000 ppfd, I think it was between 150 or 200 square feet of flowering canopy at peak can equate to almost 1 ton of cooling capacity. Obviously, that's more of a instantaneous thing that'll happen and not be consistently cooling the room. But to answer your question, no, there's no heat gain. If anything, the plant's transpiration rates offset, or help the cooling capacity that's required. Then, Nate, you want to talk about the lights and the driver
Yeah, I mean,
losses and stuff?
I guess I'm assuming this is sort of suggesting that the drivers would be mounted outside of the cultivation space in that situation. And if that is indeed the case, then we can take that percentage off. What are we talking about? 10 to 15% potentially of that overall heat load could be moved outside of the space. I think it's important to consider and make sure that that you now need to include that heat load in that calculation for whatever system is serving that space outside of it, especially if it's a common hallway, corridor, interstitial type space or something that could be open to potentially all of the flower rooms and multiple rooms of lighting at the same time. That'll start to add up. So it is important to make sure that we focus on what is inside of the space there. And if there's an opportunity to take advantage of a little bit of reduction, then that's something that can be done.
Oh, and there's also driver losses to be considered, like in LED fixtures and with HVAC fixtures, because they're not 100% efficient, right? And so there's a number of ways you can get that. You can get it from manufacturer. You can try and reach it yourself with, micromolar per joule efficiencies and PPF ratings from cut sheets. You can start calculating these driver losses. I think a 1,000-watt HPS fixture is something like 1,050 watts actually at the end of the day or something. I forget exactly.
Right.
Okay, good deal. Another question here on equipment maintenance. What should the maintenance on your systems look like? How often is it recommended? Are there any special differences between your systems and regular HVAC rooftop units?
Yeah, that's a really great question. I can jump in on that one if you like, Anders. In general, technicians that know and understand refrigeration systems and packaged systems or split systems, particularly that have hot gas reheat in them, and modulation, and as far as modulating compressors, modulating hot gas reheat valves, things like that. Obviously, that expertise really is required in order, I would use that as sort of some of the early criteria when you're vetting a particular maintenance contractor. Outside of that, of making sure that you choose the right contractor or somebody that has experience working on that type of equipment. The things that we really find, there's not a whole lot of things that are so different. In general, I feel like outside of the frequency that you would want to be involved there, particularly at the beginning of the facility startup, and really understanding and making sure that the systems are closely monitored and maintained during what would be a typical commissioning type process pre first run. And then really sort of a confirmation and almost a recommissioning or retrocommissioning of that system to make sure that through that first run, and once you plant for the second run, your system's still operating the way that it was designed and set up. And a particular item that we see often is filters loading much quicker than anticipated, or not changing out filters from the construction and having a lot of construction dust clogging filters, and not understanding why we're not getting full capacity out of the systems, near the beginning of that first flower run or halfway through the first flower run as they continue to load up. So those are some of the particular things that we really see often that would be important to follow through with and focus on. And I think in general, most preventative maintenance service agreements are typically 4 times a year, like quarterly type maintenance. I would expand that to every other month or once a month, at least for the first 6 months, to really use it as a way to get to know your service provider, have the service provider get to know you and your facility and your operation and your particular cycle and needs, both during cycles and in between cycles, and to make sure that they know if there's anything that needs to be done, whether it be any sort of warranty work or repair work that needs to be done. They'll know exactly when that can be done and can be scheduled in between runs in advance so that everybody's coordinated. Those are the sort of things that we find really, really helpful.
One last note there on that question is another good opportunity to service equipment, or good reason to, is if you're operating air-cooled DX equipment in northern climates or very cold climates, with this equipment being outside, like if it's a packaged DX, air-cooled system, and you're going to be operating that in low ambient conditions during the winter, it would be a good opportunity to service and make sure that everything is operating, up to spec before you enter those cold climate months.
Yeah, that's a great point. Yes, from a seasonal perspective, I mean, another situation is like large scale curing, drying and curing potentially that may happen. If you have more of a seasonal business where the systems aren't running all of the year, it's really important to do sort of a particular focus operation for the season, and then somewhat of a decommissioning of the system and maintenance after the season, and then again be able to repeat that cycle the following year.
Also, choose a good contractor, a good experienced contractor with the track record in commercial and industrial trades. It's so critical to the operation of your HVAC systems, particularly the way that they were installed and the quality of the ductwork and reducing the static pressure along those duct runs. And we've seen good and we've seen bad, and it can have it can play a very critical role in the performance of your facility, even if the HVAC units are right sized.
Yeah, that's really great points. I mean, it's that design is perfect on paper until you get it out and install it out in the field, right? And so you got to make sure you maintain those standards. we have a great a network of service technicians and service companies across the country that we'd be happy to refer partners to.
Absolutely. All right. Well, we only have a few minutes left. I'm not sure we're going to get to all the questions here. I apologize if we don't. And again, please feel free to get in touch with us after this webinar at any point. We're always happy to discuss the concepts of environmental control for these indoor plant environments. But here's an interesting one. What is your team's perspective on how standalone dehumidifiers / split systems measure the room temp and RH, and how does that impact the grower's perspective on how their room is operating?
Can you repeat that one more time? Was that in the chat?
It's here in the Q&A review section.
Okay.
I can. So I'll go ahead and read it
Okay.
again.
What's your team's perspective on how standalone dehumidifiers / split systems measure the room temp and RH, and how does that impact the grower's perspective on how their room is operating? So that's a good question. And standalone dehumidifiers and split systems measure the room temp. I think another way you could think of that is, regardless of the type of system measuring a room, I think what you're trying to get at is, how does the accuracy of a sensor, the quantity of the sensors in that room, and the placement of sensors affect a grower's perspective on how their room is operating? And that is a very important, a very good question and a very important point. If you have a single sensor hung in the middle of the room and you're operating, thousands of canopy square feet off that, you're not going to have a very good, statistically significant picture of what's going on in the space. So ideally, you want to have sensors within the canopy that are protected from the radiation influences of the lighting fixtures and protected from moisture or damage from staff, and aren't completely surrounded by wet plant material. We want a representative picture of what the plants are actually feeling, so as close to the canopy as possible, to get an accurate measurement. And then having a number of those throughout a room to then get an average and run your systems at is much better than operating off of, say, a thermostat that's built into a mini split hung up on the side of the wall. I mean, the conditions on the side of the wall are not what I'm trying to control. I'm trying to control the canopy. So that's where I want my sensors to be. And also, if those sensors are skewed and not near the canopy, then we're not going to get an accurate VPD calculation at all, right? And so getting those good averages from the room conditions as well as the leaf temperature and the space will get you the most accurate VPD calculation. And then also having sensors that are calibrated. We use like NIST. What were they, like NIST calibrated handhelds? These like calibrate every sensor and everything. So it's very important you're only as good as the data you collect and measure. And if you're not getting good data, then you're making bad decisions. I actually think a lot of growers' perceptions on how they were operating rooms 10 years ago, like myself, were skewed based on that information. Like, I think we thought we were running a room a certain way, but in reality, it was a way different condition than we realized, because we didn't, back even 10 years ago, sensors and controls were significantly more expensive. So now with them being more affordable, we can get better and more information cheaper and get better results.
Yeah, it's really, really exciting what the innovation is going on that side of it, and the ability to get accurate data.
Yep, it's amazing the difference between the reading from a thermostat on the wall versus a temperature sensor in the canopy. We'll read, and
throughout your space. And it's more things that we'll touch on in part 2 around sensor density and the data as well as airflow through the space. But there's really outside of going through and checking on your own periodically, you don't have a way to know how homogeneous that canopy is.
All right, well, we're a couple minutes past the top of the hour. Want to thank everybody for attending today and all of the interactive, excellent, thought-provoking questions that came up. Of course, Anders and Adrian, thank you for participating and for presenting today. If I don't know, we could stick around for another couple minutes if people felt like they wanted to stick around and continue talking. Do we want to give it another 10 minutes?
Yeah, we could do 5 or 10 more if there's other questions that folks want to throw out there. I think there was one hand that was up, and I don't remember the name. If that gentleman is interested in unmuting, we can do that, or throw it into the chat. But it's wonderful to see everybody. Thank you all for attending and spending the time with us today, and we look forward to connecting with you all soon.
Yeah, and if you have follow-up questions after the fact, please reach out to us. We can dive into them with you.
Sounds good. Well, it looks like we're losing people here now that we turned the hour. So why don't we cut it here? Again, we'll publish this. We'll publish this as soon as it's edited and ready to go. And again, please feel free to reach out. And always happy to talk about projects and talk about these concepts in greater detail.
Thank you, everyone. Really appreciate your attention and for joining us today. Thank you.
Thank you all.